What's up, my dudes? Welcome to your first taste of my flipped classroom. Woo! The crowd goes wild. So I'm out for the moment, but I make these videos for Algebra 1 pretty much every day. So I thought to myself, why don't I make some for Algebra 2? Two, that's what a ballerina wears. So we're gonna get right into it. Usually I start off every Algebra 1 class with a joke, but you guys are neither worth my time nor my energy, so we're just gonna talk about class. We're gonna talk about composite functions today. The idea behind how this structure is going to work. My hope is that you will be taking notes as we go through, but also at points throughout the video, I'm gonna tell you to pause and think or maybe try something on your own. I want you to the best of your ability to heed those directions. If I tell you to pause, give yourself 2 minutes, 3 minutes, 30 seconds, however long. Give yourself some time to work some stuff out, whether that's in your head or on paper, and then compare your answers with mine and see if what you've got is something good. And knowing you, it probably won't be. So last time we were together, we talked about functions composed of multiple functions in the form of piecewise functions. However, even though they were grouped together as different clauses of the same rule, they still worked independently of each other. Each branch of the piecewise spat out values that were unaffected by the other branches. But can we encounter functions that operate a little bit more dependently? Well, of course we can, otherwise we wouldn't have this class. Because some functions, in fact, depend on each other, which is the main idea behind what we are going to call composite functions. Now, by definition, a composite is something that is composed of multiple things. So a composite function is going to be composed, perhaps unsurprisingly in a shocking turn of events that nobody could have predicted, composed of multiple functions. So by definition, we say that a composite function is a function composed of two or more, which I'll abbreviate as 2 plus functions. And the interesting thing about composite functions is that because they depend on each other, we are going to say that the way that they are related is that the output values of one of our functions will become the input values of another function. Notationally, the way that we will express this idea of literally trying to basically plug one function into another, it will look like this. So for example, say that I want to plug g of x into f of x. Well, I'd write it as such. I'm going to swap out the parentheses for brackets because I'm doing some layers. So this function I would call f of g of x. I'm literally plugging g of x into f of x, but I could also plug f of x into g of x like so. I personally prefer this notation, but you'll also sometimes see interchangeably, f of g of x can also be written like this, kind of like an open circle. It sort of resembles the multiplication symbol, but it's not quite. They're different operations. This is telling me that I am composing the functions. For the top one, right, I'm plugging g of x into f of x, and for the bottom would be the opposite. The way, of course, that I say this, I would say either, in my first case, right, f of g of x, or interchangeably for the bottom, if I plugged f of x into g of x, I would say g of f of x. Okay, cool, we know the notation, great. But how do I actually go about arriving at these composites? So say, for example, f of x is 2x plus 4, and g of x is 6 over x. I want to find f of g of x and g of f of x. Take 30 seconds and pause the video. How do you think I might go about doing that? What's going to be the key to building my composite function? Take a risk, take a chance, see what you come up with. Go, go, go. And stop. So, if I want to compose a pair of functions, as we said above, what we're literally doing is plugging one function into another. In other words, the fancy math word for what I'm doing is just some more advanced substitution. So for f of g of x, I am literally replacing the value of x in f of x with g of x. So I'm plugging in g of x for f of x, so I could make that look something like this. F of x is 2x plus 4. So f of g of x, I'm replacing x with g of x. But g of x, we've just established, that is equal to 6 over x. So I'm substituting 6 over x into the function for x. Now all I need to do is make sure that I'm fully simplified. So can I do 2 times 6 over x? Well, yeah, 2 is like 2 over 1. 2 over 1 times 6 over x, that would give me 12 over x plus 4. So this is my composite function, f of g of x. Same thing for g of f of x. Now, in the rule for g, I am substituting in f of x. Well, g is 6 over x, and I'm replacing x with f of x. But f of x is equal to 2x plus 4. And here, again, I just need to ask, am I fully simplified? Well, notice in this fraction, I have a 6, I have a 2, I have a 4. All three of these numbers are divisible by 2. So my final function here would be 3 over 1x, or more simply, x plus 2. Fantastic. There's your idea, right? We're literally just doing some more complicated substitution. Is it annoying? Yes. But is it doable? Also, yes. Let's try it with this guy. J of x is equal to x over 2 plus 1. K of x is equal to 1 minus x squared. We want to find j of k of x and k of j of x. Give yourself 2 minutes, pause the video, talk to yourself, talk to the wall, talk to the person next to you, talk to the voices in your head. I don't care. What do you think these composite functions are going to work out to? Try it on your own, and then come back and check your work with me. Go! And stop going, I'm lonely. And I miss you. J of k of x. Well, again, I'm going to take my rule for j, which is x over 2 plus 1, and every time that I see x, I am replacing it with k of x. So this is going to become k of x over 2 plus 1. But k of x is 1 over x squared, so this would become 1 over x squared over 2 plus 1. I would say that this is totally fine. If you wanted to be annoying, though, you could keep going. So maybe I could take 1 minus x squared over 2 and try to combine it with 1 by building a common fraction. So I could rewrite 1 as 2 over 2, and then to add fractions, I add the numerators. So I could take this even further by saying that this is 1 minus x squared plus 2 over 2. And then I have some like terms that I can combine, so I could say that really this is 3 minus x squared over 2. Did I have to go this far? Absolutely not. But I hope that you can see that these two functions are just different ways of representing the same thing. Let's try it for k of j of x. Again, I'm taking the rule for k, and every time that I see x, I'm replacing it with j of x. So j of x is equal to x over 2 plus 1. When I substitute, often a good idea to use parentheses. Writing this out now, I see that this is going to be a good old classic case of met wet. So x over 2 plus 1 quantity squared really means x over 2 plus 1 times itself. And here, if I do my met wet, I would end up with something like 1 minus, well, this would become x over 2 times x over 2, which is x squared over 4. And then I have x over 2 times 1, which is just x over 2, plus another x over 2. Well, x over 2 plus x over 2 would give me 2x over 2, which is really just x. And then I have at the end 1 times 1, which is 1. Only thing I've got to do now is simplify. Well, I have a negative sign. I'm going to take my negative sign here and distribute to each of my 3 terms. This would become 1 minus x squared over 4 minus x minus 1. And 1 minus 1, I can simplify. This would become negative x squared over 4 minus x. Cool. Again, annoying? Absolutely. Doable? Yeah, probably. Quickly, just as we can compose functions, we can also decompose them. So say, for example, that I have h of x, it's equal to 3 minus x quantity squared. I want to rewrite it as the composition of two other functions. We'll call them f of x and g of x. Take 30 seconds, pause the video. What do you think the process of breaking down, reversing our composition might look like here? Alrighty. Well, let's think of the two operations that we have here. Inside of the parentheses, notice that I have a 3 minus x. And the operation here happening outside is a square. So if I think about it, I could say one of my functions here is going to be something squared. So I have that x squared accounted for. And then I also, inside of the parentheses, had that 3 minus x. Now, if I were to take this guy and write it as f of g of x, hopefully we can see that f of g of x would literally be x squared, where x is replaced by that quantity, 3 minus x. Let's do the same thing for these two down below. Take 2 minutes, pause the video, work with a partner, work with the voices in your head, do whatever you want. Let's see if we can find the functions that compose our composite function. Go ahead, have fun. And stop, that's too much fun. K of x is 7 plus cube root of 4 over x. So inside of that cube root, notice I have a 4 over x. And then outside, right, I have that 7 plus cube root. So I could take my outer function, maybe I'll call that m of x. Well, my outer function here would have been 7 plus the cubed root of something. So my input here would be x. And the thing that I inputted into that function was my 4 over x. So we'll call that 4 over x our function n of x, which tells us here, right, that the compound or composite function m of n of x, that's literally that 7 plus the cube root of x, where x was replaced by 4 over x. Same thing down below, right? Inside of my absolute value, I have that x plus 1 over 2. And then the whole thing here I can think of as my outer function. So I'll say that my outer function, u of x, would have been 5 minus 3 times the absolute value of some input, we'll call it x. And then here, the input that I used, we'll call it v of x, would have been that x plus 1 over 2. Here, same idea, rewriting this using our composite notation, u of v of x, we can see this is literally our rule u of x, where we replaced the x with x plus 1 over 2. Lovely. So we now know both how to compose and decompose functions. The last thing we want to talk about together is, well, how do I evaluate a composite function? So say, for example, I have f of x and g of x from the example above, and I want to find f of g of 3 or g of f of negative 4. What do you think that the process for evaluating these functions might look like? And as the hint, what does it actually mean to evaluate? What are we trying to do? Take 30 seconds, pause the video, take a risk, take a chance. What do you think is going to happen here? And if you've got an idea, maybe try something out. Can't hurt. Take a risk, take a chance. Who cares? Go! And stop. Well, for a composite function, the joke that I sometimes like to make about composite functions is just like ogres, and just like onions, composite functions have layers. So if I try to think in layers, then maybe it can simplify the process of figuring out what's actually happening. Let's start with our innermost layer. From there, we can work our way out. My innermost layer, notice I want to find what g of 3 is. Well, g of 3 is easy enough to find. All I need to do is take that function g of x and evaluate it when x is 3. So I have 1 minus 3 squared, which I, of course, can simplify. This would become 1 minus 9, which is equal to negative 8. Now that I know what g of 3 is, I just want to find what f of g of 3 is. But we just found that g of 3 was negative 8. So now to evaluate f of g of 3, what I'm really doing is evaluating f of negative 8. And f of negative 8, I know how to evaluate. I'm just taking my function from above. Every time that I see x, it's going to get replaced with negative 8. Well, negative 8 over 2 is negative 4, and negative 4 plus 1 is negative 3. Therefore, the value of f of g of 3 is negative 3. And I hope that you can see here that what happened is literally that the output value of negative 8 from our function g became the input value for our function f. We can do the same thing with g of f of negative 4. Thinking in layers, I'm going to start inside and work my way out. F of negative 4, I know how to evaluate. This would be negative 4 over 2 plus 1. The x in f of x is getting replaced with negative 4. Let's simplify. Well, negative 4 over 2 is negative 2. Negative 2 plus 1 is negative 1. Now I need to find g of f of negative 4, but f of negative 4 is negative 1, so what I'm really finding now is g of negative 1, right? My output from f is becoming my input for g. Well, g of negative 1 would just be 1 minus negative 1 squared. Negative 1 squared is 1, and 1 minus 1 is 0. So that tells me that g of f of negative 4 is equal to 0. Fantastic. Let's try it again with 2 more, and then you're home free. I've got a of x and b of x in the top. I've got p of x and q of x in the bottom. I want to find the values of my composite functions at the indicated value of x. Take 2 minutes, take 3 minutes, pause the video, see how far you get. Have fun. Go. And stop. So sorry for the elevator dinging in the background. It's waiting to pick me up to bring me down to hell. Okay, a of b of negative 4. Again, I want to think in layers. So let me start by finding b of negative 4. Well, b of negative 4 would be equal to 1 over negative 4 plus 3, just substituting negative 4 in for x in our function b. Negative 4 plus 3 is negative 1, so I have 1 over negative 1, which is negative 1. Now, I need to find a of b of negative 4, but we just found that b of negative 4 is negative 1. Evaluating this guy, I now just need to find the square root of 7 minus negative 1. Well, 7 minus negative 1 can be more simply written as 7 plus 1. So this is equal to the square root of 8. And then thinking back to our properties of radicals, the square root of 8 can be reduced as the square root of 4 times the square root of 2, which tells me that 2 root 2 is my final answer. Cool. For b of a of 7, again, working inside out, I should say. That's a pretty good movie. A of 7. Well, that would be equal to the square root of 7 minus 7. 7 minus 7 is 0, and the square root of 0 is 0. Taking this output value from A, I now want to plug in to B, so I'm going to find B of 0. Well, B of 0 would be 1 over 0 plus 3. 0 plus 3 is 3. And I can't simplify further. 1/3 is the value of my composite function. Cool. P of x is equal to negative 2, absolute value of x. And q of x is quantity x minus 5 cubed. So I'm going to, again, think in layers. Let's start by finding q of 2. Well, q of 2 would be equal to the quantity of 2 minus 5 cubed. 2 minus 5 is negative 3, and negative 3 cubed is negative 27. Now I'm taking the output value from Q and plugging into my function P, so I now need to find P of negative 27. Well, P of negative 27 would be negative 2 times the absolute value of negative 27. The absolute value of negative 27 is positive 27, and negative 2 times 27 is negative 54. For Q of P of 0, again, working inside out, I'm going to start by finding P of 0. Well, P of 0 would be negative 2 times the absolute value of 0. The absolute value of 0 is 0, and negative 2 times 0, unsurprisingly, is 0. Last but not least, I just need to now find Q of the output value of P, which we just found was 0. Q of 0 would be the quantity 0 minus 5 cubed. Well, 0 minus 5 is negative 5, and if I cube negative 5, I get negative 125 as the value of my composite function. Congratulations, you now know everything that you need to know about composite functions. Look at you, you did it. So I'll see you next time for our next video where we'll talk about domain. But until then, take care, be good, which I know is hard for you. Do something nice for somebody else. Don't hurt anyone, don't burn down the building. And I'd say I'd miss you, but that would be a lie. See you when I see you.